The Moon is a unique body. There is no place on Earth that offers a topography quite like it. Certainly, the Earth has features similar to those on the lunar surface. But nowhere is the Earth cratered to the extent and in the same manner as the surface of the Moon. Where can men go to test and practice the exploration techniques being developed for Apollo landings? The United States Geological Survey decided to build a model of one part of the lunar surface in an area accessible to present research centers. Examining a multitude of lunar photographs taken by the orbiter satellites, survey scientists choose proposed Apollo landing site 2P6 in the southwest part of Mare Tranquillitatis as a representative area and one that would be profitable to reproduce. Where to build it? Near Flagstaff, Arizona, are fields of volcanic cinders, the result of eruptions about the year 1065. The cinders provide an excellent material to recreate the lunar surface, and the geologic structure will offer training in mapping and sampling for astronauts. Craters on the lunar photos have been carefully examined, and their relative ages charted. All the craters are separated into three major age categories, from oldest to youngest. Of the 426 craters larger than 2 meters across that can be seen on the photos, 354 are among the oldest, 61 are of intermediate age, and 11 appear to have been formed recently. An area covering over 268,000 square meters is chosen and fenced off, and construction of the crater field begins. First, the ground is prepared by dragging to clear away the underbrush and to produce as smooth an original surface as possible. It will be important not only that the craters are reproduced in the same size and approximate age relationships as on the lunar surface, but that the material ejected from them creates a surface similar to that on the Moon. So all the existing bumps and irregularities are smoothed out. Then a surveying team carefully locates the center point of each crater visible on the orbiter photographs, and stakes are driven to mark the position. Each stake is color-coded so that the craters of the three different ages can be identified. Finally, all the craters have been positioned and marked as old, intermediate, or young in age. Placing explosives in holes at the right location and blowing them in the right order to match the age sequence is not all that is required to recreate a portion of the Moon's surface. The composition of the cinder and clay material is carefully studied to determine what size charges to use and how deep to bury them, so that each crater will be, as nearly as possible, the same size as its lunar counterpart. After weeks of study and calculation, these values have been computed for each of the 426 craters. We are ready to dig the holes. As the backhoe slices into the ground, it exposes the variety of materials that make up the cinder lake. Cinders from nearby craters have fallen over the area at different times. Between some of these pyroclastic episodes, brown clay was deposited. The result is layers of clay and layers of cinder from different eruptions. In some places, the cinders fill pockets in the clay. Great care is taken to dig the holes at precisely the depth calculated by the explosives expert. As the appropriate depth for each charge is reached, the last few scoops are removed one at a time, and measurements taken between scoops. Now that the different layers of geologic units are exposed by the backhoe, a geologist can conduct a detailed stratigraphic study in the deepest of the charge holes. The result of his study will be a control on geologic traverses conducted here. During most testing of lunar procedures, the test subjects have not previously studied the area. Besides testing techniques and tools, they attempt to define the geologic formations in the region. So this geologist carefully describes the different layers, their thickness, their composition, a valuable check on the accuracy of the test subject's geologic analysis. Not only are we creating an area that very closely resembles a portion of the lunar surface, but an area which should present geologic problems analogous to those an astronaut will encounter on the moon. Once the geologist has completed his work, the final preparation of the field for explosions can be made. 426 holes await the emplacement of explosives. Boosters are prepared, which will be used to set off bags of nitrocarbonitrate. Each hole is loaded with a size charge calculated to create just the right size crater. The bags of explosives are positioned with care and the boosters inserted. Primer cord is attached to the boosters and held out of the way while the hole is filled. One after another, all the charges are laid, even though different craters will be fired at different times. 426 explosive charges, 426 craters in the same position and of the same size as one part of the moon's surface, if the amount of explosive has been correctly calculated, if the depth of each crater is correct, if the surveyors have accurately reproduced the crater positions. Finally, all the explosive charges are in place, and the holes have been covered over. Once more, the field is dragged back and forth until it is smooth again. All that can be seen are stakes marking the position of the primer cords. One by one, 354 of the charges are tied together and the stakes removed. These will be exploded first. The ejecta and debris will spread out over the surface to be covered by later explosions, and so they will represent the oldest craters in one part of the moon. Primer cord is a unique firing device. Connecting all the charges to the firing box, it burns with such speed that a piece of it laid across the country would burn out in Los Angeles only 13 minutes after it was lit in New York. One after another, all the charges to be fired in the first shot are tied together. Several months have gone by since this area was selected and fenced off. Hundreds of man-hours have gone into the calculations and careful preparation for firing. And now we are ready. Give us 354 old-age craters.
10, 9, 8, 7, 6, 5, 4, 3, 2, 1, fire!
Now we need 61 craters of intermediate age. Here's the same detonation recorded by high-speed cameras rolling at 5,000 frames per second. They show the primer cord tracing paths to each of the 61 shot holes. Later, the 11 youngest craters are exploded. As each set of craters has scattered debris over the surface, we have created an altogether new geologic area, with the oldest ejecta on the bottom and the newest on top. In some places, the original layers of cinder and clay have been completely turned over. We have changed a rolling cinder field into a crater field. But how closely does it match the topography of lunar site 2P6? This is the orbiter photograph of the lunar surface. And this is an aerial photograph of the new crater field. The size and location of each of the 426 craters have been reproduced with remarkable accuracy. On this crater field, astronauts will be able to train in a more realistic setting. A setting like the lunar surface. A little of Mare Tranquillitatis, here in Flagstaff, Arizona.